Welcome all. Today we will discuss a special class of modules. We call these modules as injective modules. So first we will prove a theorem which gives 4 equivalent conditions, and then we will define injective module, so satisfying one of those 4 equivalent conditions. And then we will see Baer's criterion. It says how we can verify an R module whether it is injective or not. And then we will see some examples of injective and non-injective modules, and at the end we will prove that any R module, it is contained in some injective R module. So you consider an R module M, then you can have an injective R module Q such that from M to Q you can have injective module homomorphism. So that might be the reason we call this class of modules as injective modules. So here is the theorem. So you consider an R module Q, then for any R module we can have 2 functors, home functors, and one of them was this quantavariant functor. So we have proved that this quantavariant functor, it is always left exact. What is the meaning of that? So you consider a short exact sequence, then after applying this functor you will get a left exact sequence. So I mean that you will get an exact sequence like this where it is exact at this point and at this point, but we do not know about this point. The question is, can we extend this thing further to a short exact sequence or not? So in general it is not true. For an R module Q, if you apply this functor to a short exact sequence, you may not get a short exact sequence, but you can get an exact sequence like this. Now if we get so after applying this functor on a short exact sequence, if we get another short exact sequence, that means if we can extend this thing further, then that R module, it is special, and then that R module Q, we call it injective R module. So since this functor, it is always left exact, this functor, it preserves exactness on the left side, means it preserves exactness at these 2 points. But if it preserves exactness on the right side, it is equivalent to say that this functor is exact functor. So statement 1 and statement 2, these are equivalent. It follows from the fact that this functor, it is always left exact. So you consider a short exact sequence and you apply this quantavariant functor, you will get an exact sequence like this. So this is exact if and only if you can extend it to a short exact sequence, and it is equivalent to say that if you consider an injective module homomorphism, then we should get a surjective module homomorphism, this one. So this module homomorphism, it is induced by this module homomorphism. So this is injective module homomorphism, and we should get a surjective module homomorphism. Then only this functor is exact functor, and then only it preserves exactness on the right side. So statement 1 and 2, these are equivalent. It follows from the fact that this functor, it is left exact functor. And statement 3, just another way of saying statement 2. So here again you consider an injective module homomorphism, that means this is exact sequence, and then so statement 2 is saying that this induced map, that should be surjective. So what is the meaning of that? So you consider any element here in the codomain, you should have a pre-image here. So there should be some G, a module homomorphism from M to Q here, whose image is F. Now what is this map? So if we analyze this map, so if we recall this map, it is just phi. If you apply this map on G, it is just G compose phi. So if image of G is F, it is equivalent to say that this composition is same as F. So in terms of diagram, it says that for any injective module homomorphism phi, for any R module homomorphism F from L to Q, one should have an R module homomorphism from M to Q such that this diagram is commutative. So this diagram is commutative means you come this way, it is just G compose phi, that should be same as F. So these 3 statements are equivalent, it is easy. And next we will consider this statement. it says that every short exact sequence starting with Q, that should be a split short exact sequence. So in general, a short exact sequence that need not be a split short exact sequence. But if a short exact sequence starting with a particular module Q, if it is split short exact sequence, then that kind of R module, it is special R module. And so we prove that statement 3, it is equivalent to statement 4. So first we will prove this implication. And how to verify whether a short exact sequence is split short exact sequence or not? If we recall, one of the equivalent condition, it was that if it has a splitting homomorphism from M to Q, let us say lambda, such that their composition is identity on Q. And it is equivalent to say that there exists a splitting homomorphism from N to M, such that their composition is identity on N. So we will work with Q only, from Q to Q. So in this case, we will consider just identity map on Q, because we want splitting homomorphism from M to Q. So splitting homomorphism means those homomorphism whose composition is identity on Q. So that is the reason we are considering this identity morphism. And then we will use this statement. It says that for any injective module homomorphism from L to M, and for any module homomorphism from F to Q, one should have a module homomorphism from M to Q. So we have this structure. Now using this statement, one can say that there exists lambda, a module homomorphism from M to Q, such that this diagram is commutative. And what is the meaning of that? So lambda compose phi, that should be identity on Q. And this lambda will give us the splitting homomorphism. So therefore statement 3, it implies that the short exact sequence starting with Q, it is a split short exact sequence. Next we will prove condition 4, it implies condition 3. So this proof is something non-trivial, and here we will use push out of two morphisms. So we have this condition and we want to verify this condition. Okay. So suppose we have this structure, that this is an injective module homomorphism from L to M, and this is an arbitrary module homomorphism from L to Q, and we want to prove existence of such map. So we have this structure here. This is injective module homomorphism and this is an arbitrary module homomorphism. We just want this map. Okay. So we consider push out of two module homomorphisms phi and F. And what is push out? So it is just R module W along with these two module homomorphisms, alpha from M to W and another one is beta from Q to W, such that this diagram is commutative. So you come this way or you come this way, both are same. So how to construct such module along with these module homomorphisms? So here is the way. So you consider these two module homomorphisms, and then we consider direct sum of M and Q. So it is this direct sum, and then we consider a submodule of this direct sum. So namely, for each element in L, we can get an element. But just by considering this map, we can get an element of M, it is phi of x, and considering this module homomorphism, we can get an element. So here we consider minus f of x. So for each x belongs to L, we can consider this tuple where first component it is phi of x and second component is minus f of x. So this is a subset of this direct sum and it is non-empty subset because 0, 0 it is there, and one can verify that this subset it is closed under addition and scalar multiplication. So using the fact that both phi and f, these are module homomorphisms, one can verify that if you consider two tuples like this and you add them, then that is also there in this subset. So this is a submodule of this direct sum, and then we consider the corresponding quotient module. So it is M direct sum Q modulo V. So this is our W. So next we want to have this module homomorphism. So we define, so from M to M direct sum Q, we can have natural module homomorphism, namely y is going to y, 0, and then from M direct sum Q, so M direct sum Q to this quotient module, one can consider y comma 0 its equivalence class. So composition of these two maps will give alpha. So it is just mapping y to y comma 0 its equivalence class in this quotient module. Similarly, one can have this module homomorphism. So it is mapping any element z to 0 comma z its equivalence class in W. So then this preserves addition and scalar multiplication. So this beta, it is a module homomorphism, and by the construction this diagram will be commutative. So for example, if we just consider let us say x, so here it is phi of x and here it is f of x. So then it is going to phi of x comma 0 its equivalence class, and this one is going to 0 comma f of x its equivalence class. So are they equal? Yes, because so why these two elements are, these two equivalence classes are same? Because the difference between this tuple and this tuple, it is there in V. So going modulo V, their difference going modulo V, that will be 0. So equivalence classes of this tuple and this tuple, it is same, because their difference, it is an element of V. So therefore we have an R module W along with this module homomorphisms such that this diagram is commutative, and that R module we call it push out of these two module homomorphisms, and we will use this thing. So using this, our proof is easy. So we want to use this statement. It says that any short exact sequence starting with Q, that is split short exact sequence. So here we consider this push out of W, and from Q to W we have a morphism. So once we prove that this is injective module homomorphism, then this module homomorphism, it induces a short exact sequence like this, and we can use this statement. So question is it injective module homomorphism? Yes. Since phi is injective module homomorphism, one can verify that this beta, that is also injective homomorphism. So we can verify here. So suppose Z is going to, so 0 comma Z its equivalence class, a module of V, and suppose this is 0 element, so equivalence class of 0. So what is the meaning of that? So meaning this, that this tuple, it is an element in V, and that means it should be like phi of x comma minus f of x for some x belongs to L. So then this first component phi of x, that should be same as 0, and it implies that x should be 0, because phi of x is 0, that implies x is 0, as phi is injective. So this map, it is injective. So therefore x is 0, and once x is 0, then this second component z, it is just minus f of x, that should be 0. So in this way one can verify that this module homomorphism, it is injective module homomorphism. So this injective module homomorphism, it induces this short exact sequence. So here this is just natural projection map from W to co-kernel of beta. So next you consider this short exact sequence, and by the given condition 4, it is starting with Q, so it should be a split short exact sequence, and that means there should be a splitting homomorphism from W to Q. So our ultimate goal was to prove that there exists a module homomorphism from M to Q such that this diagram is commutative. So at least we have a module homomorphism from M to W. Once we have a module homomorphism from W to Q, so we can take their composition to get a module homomorphism from M to Q. So since this is split short exact sequence, we have this splitting homomorphism lambda, that is a module homomorphism from W to Q such that this composition lambda compose beta is identity on Q. We will use this lambda. So we set G, that is lambda compose alpha. So first you take lambda alpha and then you take lambda. So it is lambda compose alpha, and then we need to verify that this map G, it is just composition of alpha and lambda. that will give us that desired homomorphism. So we need to verify that this diagram is commutative if we consider G. So G compose phi, it is just, so definition of G, it is just lambda compose alpha. So it is compose phi, and then alpha compose phi. So this one, it is same as beta compose F. So it is beta compose F, and since lambda compose beta is identity, it is just F. So we have a module homomorphism G from M to Q, this one, such that G compose phi, it is just F. So this diagram is commutative. So statement 4, it implies statement 3. So we have these 4 equivalent conditions, and next we prove, next we define an R module Q. It is called injective R module if it satisfies one of these equivalent conditions, and hence all the equivalent conditions. And here we will see why we call this as injective module. So one of the equivalent condition was that any short exact sequence starting with Q, that is a split short exact sequence. And the meaning of split short exact sequence is that this middle one, it is that should be isomorphic to this direct sum, this one. So the terminology injective, it comes from the fact that any module M into which Q injects has Q as a direct summand. So you consider an injective module homomorphism from Q to any R module M, then it is just saying that then this Q, it will be just direct summand of M. So because this injective module homomorphism, it induces this kind of split short exact sequence, and by the splitting I mean M, it is just isomorphic to Q direct sum co-kernel of, so something, Q direct sum something, co-kernel of phi. So this injective module homomorphism, it behaves like Q to this thing. So x to here x comma 0. So it is saying that any injective module homomorphism phi from Q to any R module M, it behaves like this kind of embedding. Or in other words, any R module M into which Q injects has Q as a direct summand. So that is the reason we call this R module as injective R module. Criteria. So how we can verify whether certain R module, whether it is injective or not. So one of the equivalent condition was that this R module Q, it is injective if for any injective module homomorphism phi from L to M, and for any module homomorphism F from L to Q, we should have a module homomorphism G from M to Q such that this diagram is commutative. So this condition, it is equivalent to say that you consider any submodule L of M. So M is an arbitrary R module, and suppose L is a submodule of M, then it is saying that for any module homomorphism F from L to Q, we should have a module homomorphism from M to Q G such that this diagram is commutative. So it is basically saying that any module homomorphism from this submodule L to Q, it can be extended to a module homomorphism from this R module M to Q. So in other words, for any module homomorphism F, there should be G such that this diagram is commutative. It is equivalent to say that G restricted on L, it is same as F. So this was one of the equivalent condition of injective modules. And here we verify that it is enough to consider this special case only. So you consider R as a module over itself, and you consider an ideal I. So then for any ideal I, you can have this inclusion map. So it is enough to verify that for any module homomorphism from this I to Q, one should have a module homomorphism from R to Q such that this diagram is commutative. So basically G restricted on I, that should be same as F. So since this is special case of this one, so this implication is trivial, and next we want to verify this implication. So suppose we have this special case that any module homomorphism from this ideal to Q, we can extend it to a module homomorphism from R to Q. Suppose we have this special case, we want to verify this general case. So here we consider so L is a submodule of M, and suppose F is a module homomorphism from L to Q, and we want to prove that there exists G. So we show that there exists G such that G restricted on L, it is F. So what we do, we just consider this collection, and this is just collection of tuples like this, where first one, so second one, it is just R module lying in between L and M, and first one, it is just R module homomorphism from that R module L prime to Q, such that if you restrict this module homomorphism on L, then it should be F. So now question is this collection non-empty? So answer is yes, it is non-empty, because you can just consider F comma L. So L is lying in between L and M, and of course if you consider F, so its restriction on L, it is the same thing. So trivially we have this element in this collection. So this collection is non-empty, and we want to prove that this is a partially ordered set. So we should give a partial order, we define a partial order on this set in this way. What is that? So suppose we have two tuples like this, then this tuple, it is less than or equal to this second tuple if we have containment relation on this thing. So if L prime, it is a submodule of L double prime, and if we restrict this module homomorphism, so it is a module homomorphism from L double prime to Q. So if we restrict this module homomorphism on L prime, we should get F prime. So that is the relation, and one can verify that this gives a partial order, and therefore this is a partially ordered set with respect to this partial order, and it is non-empty because this thing is there trivially. So then we should apply John's lemma. So to apply John's lemma, one should verify that any totally ordered subset of this collection, it should have an upper bound in this collection. So if you consider a totally ordered subset, you can just take their union L alpha, that will be your second component, and first one, so it is G. How you define G? So it should be a module homomorphism from this union to Q, and how we can define? So for each element in this union, so this element should come from at least one L alpha, and you just use that corresponding map. Okay. So in this way, one can verify that any totally ordered subset of this collection, it has an upper bound in this collection. So we can apply John's lemma. So by John's lemma, S has a maximal element. So maximal element like this tuple, where this one, this is an R module lying between L and M, and this is a module homomorphism from M prime to Q, such that if we restrict it on L, then we should get F. So we have this condition, and this is a maximal element in this collection. So it is enough to verify that M prime is same as M, and once we prove that M prime is same as M, then this G, it is a module homomorphism from M to Q, and its restriction on L, that will give F. So that was our desired module homomorphism G. So we prove that this maximal element G comma M prime, so this M prime, that should be same as F. So here is the proof. If possible, suppose M prime, so M prime is lying between L and M. So M prime, this is a subset of M. So if possible, suppose these are not equal. So M prime is not same as M. So then there should be some element M in this module M, but not in M prime. So we will work with that element. So considering this element, we can consider this ideal. What is that? Because we have this condition in terms of this ideal. Okay. So here we consider this ideal. It is just collection of all those elements of the ring R such that R times M, it is an element in M prime. So M is an arbitrary element of M. If you multiply it with R, so that is an element of M. So if it lies in M prime, then we collect that R. So it is collection of R such that multiplying R with M, we should get an element of M prime. So is this collection non-empty? Yes, because 0 element is there. If we multiply 0 to M, we get 0 element of the module and it is there in M prime. So this is non-empty collection and one can verify that it is closed under addition and multiplication by any element of the ring. So this is an ideal of R, one can verify that. And next, so we consider this ideal. So from ideal to R, we have that inclusion map, and then we consider a module homomorphism F from I to Q. So we define a module homomorphism from I to Q in this way. So G is a module homomorphism from M prime to Q. So using G, we define a module homomorphism from I to Q. Here is the way. So H of R, it is defined to be G of R times M. Because if we take R from this ideal I, then R times M, this is an element of M prime, and then we apply G. So then one can verify that this map H, it preserves addition as well as scalar multiplication. So therefore, this is a module homomorphism from I to Q. And by the hypothesis, by this thing, now there should be some extension map. So we denote that extension map as capital H. Okay. So by the hypothesis, H can be extended to an R linear map. Let's say H. That means if we, so H is a module homomorphism from R to Q such that if we restrict this H on this ideal I, it is small h. So next, using this thing, so we have assumed that M prime is not same as M, so we should get some contradiction. So we want to construct an R module, submodule of M. Here it is something bigger than M prime, and that will contradict this fact that this tuple, it is a maximal element. So here we proceed in this way. So you consider G, it is a map from this R module. So since M is an element of M, so if we consider M prime plus R times M, so this is just submodule of M generated by M prime as well as this element M. So we are attaching one more element in the generating set. So this is a submodule of M and it is something bigger than M prime, because this element, it is not there in M prime. And next we want to define a map from this R module to Q. So we define in this way. So any element here, it looks like x plus R times M. Then we define G of x plus R times M in this way. So x is an element of M prime. So we have this map G. G is a map from M prime to Q. So we can use that. So it is G of x plus this R we will use. So this R, it is an element in the ring. So and H is a module homomorphism from R to Q. So we use that H. So it is defined G of x plus Rm, it is defined to be G of x plus H of R. So we should prove that this is well defined map. So suppose x plus Rm, it is same as y plus Sm, let's say. So then x minus y, it is same as S minus R times M, and both this x and y, these are elements of M prime. So their difference, it is there in M prime. So therefore this is an element in M prime, because this is an element in M prime. So thus this difference S minus R, this is an element in this ideal. Okay. So what we do here, it says that if we apply G now, so G of x minus y, that should be same as G of S minus R times M. And what is G of S minus R times M? H of R, it is defined in this way. So this one, G of S minus R times M, it is just H of S minus R. But so S minus R, this is an element in ideal I. So we can use this map, but we cannot split it here now. So what we do, so this is same as capital H of S minus R, and then capital H is a module homomorphism from R to Q. So since capital H, this is a module homomorphism, it preserves addition H of S minus H of R. So basically we are getting G of x plus H of R, it is same as G of y plus H of S. So this map G, it is well defined map, and one can verify that it preserves addition and scalar multiplication, because small g and h, these are module homomorphisms. So using that, one can verify this capital G, this is a module homomorphism from this submodule of M to Q. And by the construction, if we restrict this map G on M prime, small g. So therefore, so if we G comma M prime plus Rm, it is something bigger than G comma M prime, this thing. So this contradicts the maximality of this tuple, and this contradicts the assumption that M prime, it is not same as M. So therefore M prime is same as M, and then this G will give a module homomorphism from M to Q whose restriction on L, that is F. So assuming this condition, we have verified this condition. So we have proved this theorem. It says that an R module Q is injective if and only for every left ideal I of R and any R linear map H from I to Q, that this module homomorphism from I to Q, it can be extended to an R linear map capital H. So I should write capital H here from R to Q such that this diagram is commutative. So it is equivalent to say that H restricted on I, it is same as F. And yeah, so far we have given the equivalent conditions of injective modules, but now we want to see some examples of injective modules. So an existence of injective modules, it is something non-trivial. So we should prove this corollary, and using this corollary we can have many injective modules. So how to find injective modules over a PID? So this corollary, it is saying that over a PID, an R module, so if R is PID, then an R module Q, it is injective if and only if it satisfies some condition. We call those modules as divisible modules. So here we define divisible modules. So an R module Q, it is said to be divisible if Q is same as R times Q for every non-zero element in the ring. So for every non-zero element in the ring, let us say R times Q, this is a submodule of Q. So there is no guarantee that this is same as Q, but if these are equal for any non-zero element in the ring, then we call those modules as divisible modules. So in some sense, we can divide our module by any non-zero element of the ring. That is the reason we call it divisible module. And here we prove that over a PID, an R module Q is injective if and only if it is divisible. because it is injective if and only if it satisfies this Baer's criterion. So it says that for any ideal I, you have this inclusion map. So for any ideal I and for any module homomorphism F from I to Q, you can have a module homomorphism G from M R to Q such that this diagram is commutative. So such that if you restrict G on I, it is same as F. This is Baer's criterion. And what is divisibility thing? So for any non-zero element R, this submodule R times Q, that should be same as Q. So let's prove why these two conditions are equivalent and where we can use this fact that R is a PID. So since R is a PID, any ideal here, it is just principal ideal. So it is generated by a single element. Let's say suppose this ideal I, it is generated by R. Then for any module homomorphism F from I to Q, we can have this element F of R, this is an element of Q. We just want to have some module homomorphism such that this diagram is commutative. And how to find a module homomorphism from R to Q? So any module homomorphism from R to Q, it is uniquely determined by the image of 1. So it is enough to find the image of 1. So existence of G such that this diagram is commutative, it is equivalent to say that there exists an element like G of 1 such that if we restrict this map on I, we should get F. So what I mean that, so this R times G of 1, it is just G of R, and since R is an element of I, that should be same as F of R. So for any module homomorphism F, there should be some module homomorphism G such that this diagram is commutative. It is equivalent to say that for any element like this, there should be some element in Q such that F of R, it is same as R times G of 1. So we can see that why these two conditions are equivalent. So this thing is saying that you consider any non-zero element R, then for every element in Q, there should be some element in Q such that X is same as R times Y. So here for any element in Q, you should have another element in Q such that F of R, it is same as R times G of 1. So we can see why these two conditions are equivalent. And this gives that, so this condition is satisfied, it is equivalent to say that this module is injective, and this condition is satisfied, it is equivalent to say that your module is a divisible module. So we have proved that over a PID, an R module is injective if and only if it is divisible. And then we can have this particular case because Z, this is a PID. Okay. So a Z module, it is injective if and only if it is divisible. So over Z, how to find injective modules? So we just have to collect divisible modules. So here are some examples. So if you consider Z over itself, is it divisible module, divisible Z module? No, it is not divisible Z module because you consider N something non-zero. Then what is N times Z? It is not same as Z. As a module over itself, it is not divisible. Therefore, it is not injective module over itself. So Z, it is not injective Z module. And over a PID, every quotient of an injective module is again injective. Why? Because every quotient of a divisible module is again divisible. So suppose your R is PID and you consider a divisible module. So for r not equal to 0, suppose q is same as r times q. Suppose you have this condition. Then if you consider a submodule of q and suppose you consider this quotient module, is it divisible? Answer is yes, because for any non-zero element r, you can just so if you consider r times q mod k, it is just r times q plus k modulo k. Since r times q is same as q, so this is just q modulo k. So something is divisible, it implies that its every quotient module that is also divisible. So therefore over a PID, something is injective, that implies that its quotient module that is also injective. So both q and q mod z, these are divisible z modules. Why q is divisible z module? So this collection of rational numbers, because you consider any non-zero integer, so n is non-zero, then n times q, this collection of rational numbers, it is same as q. Because you consider any element p by q, you can always write it as n times p by nq. So this collection of rational numbers, this is a divisible module over z, and hence its quotient module q mod z, that is also divisible z module, and therefore this q and q mod z, these are injective z modules. And next we prove that every R module, it is contained in some injective R module. So first we will prove this result for Z modules. So here we prove that every Z module, it is contained in some injective Z module, or in other words, every Z module, it is a submodule of some injective Z module. So here you consider a Z module M, and we want to prove that this is contained in some injective Z module. So here is the way. So every module, it is quotient of a free module. So that we have proved. So you consider any module, let's say M, then you can have a free module, and from that free module to M, you can have surjective module homomorphism. So therefore this M, it is just you can think it as quotient of a free module. Since you are considering Z module, you can have a free Z module F, such that this M, it is quotient of that free Z module. So M is same as F modulo K, where F is a free Z module. And how does it look like a free Z module? It is just direct sum of Z, some copies, that is indexed by some set gamma. Okay, it can be finite or infinite. Okay, so then this M, it is just this quotient module, and it is just this free Z module modulo some module. And then this quotient module, it is contained in this quotient module, because this free Z module, so it's like Z power n, it is contained in q power n. So you can take direct sum of arbitrarily many copies of Z. So then also this free Z module, it is contained in this direct sum of q, that many copies. So this thing is contained in this as a Z module. So therefore their quotient, that this quotient module, it is contained in this thing, where K, it is a submodule of this, and hence it is a submodule of this Z module. So we have this containment relation, and next one can see that this is a divisible Z module. Why? Because Q is divisible Z module, and hence their direct sum, some copies of Q, this direct sum, that is also divisible Z module, one can verify that. So then this quotient module, that is also divisible Z module. Since it is divisible Z module, it is injective Z module. So this Z module M, it is contained in some injective Z module. This is the proof. And next we prove this result for any arbitrary ring. So here you consider an arbitrary ring R, and then we prove that every R module, it is contained in some injective R module. So here is the way. So we prove the result only when R is commutative, and for non-commutative case also proof is same, but we have to be bit careful. Okay. So you consider an R module M, and we want to prove that M is contained in some injective R module. So what we do, we just first we consider this M as a Z module, because what is M? It is R module, that means you have addition and R scalar multiplication. So with respect to addition, it is abelian group. So therefore this M, it is just a Z module, just you consider that addition, and then you can give Z scalar multiplication, you can define in a natural way. So therefore this M, it is in particular a Z module. So considering this M as a Z module, by the previous corollary, M is contained in some injective Z module, let us say it is Q. Then we consider this isomorphism. So we have proved that any, so this was one of the exercise, that any R module M, it is isomorphic to Hom of R comma M, and how to get that isomorphism. So you consider any element X, and then we want to construct a module homomorphism from R to M. So any module homomorphism from R to M, it is uniquely determined by the image of 1. So if we define this mu X just by sending 1 to X, then it is just giving a map sending R to R times X. So this is a map given by multiplication with X. So then one can verify that this is an isomorphism. So therefore we have this isomorphism. So the R module M, it is isomorphic to this Hom, this R module. And next we should see that this is collection of R module homomorphisms from R to M. So therefore this is a subcollection of this thing, and what is this? This is collection of Z module homomorphisms from R to M. And what is Z module homomorphism? So it is just a map from R to M which preserves addition. So since any R module homomorphism, in particular any R module homomorphism, it preserves addition. So therefore any R module homomorphism from R to M, it is in particular a Z module homomorphism from R to M. So we have this containment relation. And next we see that this module, it is contained in this one, or we can have an injective module homomorphism. Why? Because this M, it is contained in Q. So M is contained in an injective Z module Q. So we have this inclusion map from M to Q, and then if we apply this left exact functor Hom of R comma blank over Z, if we apply this left exact functor, then so since this is injective map, after applying this left exact functor, again we will get an injective map. So we get this injective module homomorphism. So thus this M, it is contained in this thing, and one should verify that this containment, it is actually giving an injective R module homomorphism. And then the result follows from the fact that this is an injective R module. So this is something non-trivial. One should prove this exercise that if Q, this is injective Z module, then this Hom of R comma Q over Z, one can give an R module structure on this, and that R module, it is injective R module. So in this way, this M, it is contained in this injective R module. So that proves this theorem. So this result, it is just the counterpart for injective modules of the fact that every module, it is a quotient of a projective module. So in case of projective modules, so we have this result. You consider an R module, then there exists a free R module F such that from F to M you have this projection map or surjective module homomorphism. Okay. So in case of injective thing, what we are proving here, that for any R module M, you can have an injective R module, I should denote it as Q prime, and from M to Q prime you should have injective module homomorphism. Okay. So that is the reason I said here that this result, it is just counterpart for injective modules of the fact that every module is a quotient of a projective module, because every free module, it is projective module.